Hello everybody, welcome to my dorm desk, which has also in the last few days become a sort of a electronics lab. Today I want to show you a little project I've been working on for some extra credits at university, which is an Arduino which draws vector graphics on an oscilloscope. So basically at the start of the year our physics professor told us we can make one of various projects, and the one I liked most from the list was this one, Arduino plus oscilloscope, anything we want to do which uses both of them. And when I saw that, I immediately thought of like the oscilloscope graphics you see every now and then on the internet. And hey, I wanted to try that. Now, since the whole COVID bullshit is in full swing currently, I couldn't use the oscilloscopes at my university's labs, so I just bit the bullet and bought one, the cheapest I could find that had all the capabilities necessary, especially this external X input, or the XY mode as it is called on other oscilloscopes. This also comes with a cost of it being like really old. Telequipment D54s were fabricated, started being built in like 1970, and yeah, this one is from 1971. Telequipment is actually the name Tektronix used in Europe a long time ago. It still works, but it's seen better times, right? I'm most sure that it was dropped a few times over its lifetime, right? You can see the dents here, the paint is scratched here, one dial was missing and I had a friend 3D print me it, but you can also see it's sort of bent, it's off center, and as well as some, like this banana plug is off center, the whole face is warped. But it works for what I'm gonna use it, so yeah, it's great from that standpoint. Right, so let's first quickly take a look at what oscilloscopes are like used for normally, not this sort of bullshit I'm doing. I just started it and it's gonna take like 15 seconds for the cathode ray tube to boot up. Well, boot up, such a modern word, like heat up. Okay, and while it's heating up, I'm gonna grab the probe and put it. Okay, and we have a point, and because it's in XY mode it stays put, but right, if I it's weird, okay, let me put it on ground. Cool. So now I'm watching the second channel, which is this stuff over here. And from here I can change how fast that dot sweeps over the screen, right? Like I can have it really slow, or I can have it ultra fast. Now it's 0.2 microseconds per sweep, very fast. But I'm gonna set it to something like this, right? It's a little bit flickery. And I want to show you a few examples of signals we can analyze on the oscilloscope. The dumbest one, which I first discovered, was that if you touch the probe, your body sort of acts like an antenna and induces 50 hertz noise from the, like, my body is basically absorbing 50 hertz from the mains current all over the room, and when I touch this, if it wasn't set on ground, if I set it on DC, we can see some noise over there. And I'll change the scale so that it's all in frame, change it some more. There we go. Right, and I can change the time scale as well. And we can see the signal I am inducing. This is a pretty dumb example. I have a better one with this extremely cheap multimeter. It's like 5 euros. But it has this nice signal generator feature. I think it's used for like checking like audio amps and whatnot. And I will, it basically puts, I think, 10 or 100 hertz signal, 1 volt signal across the its two probes. And if I connect the positive, yeah, give me 1 second. Right, that's it. I connected the positive to the positive and negative to the ground of the oscilloscope probe, and we can see a square wave over here. I can play around with the time scale a little bit, maybe make it more continuous, and possibly also sync the oscilloscope's beam with the signal to get a stationary curve, but I don't think I'll be able to do that. Maybe play around with the gain. Oh, I got something. Greater stability. I do not actually know what I'm doing with these knobs. I've been playing around with them and sort of have a small bit of intuition of what each one does. Like, the names are sort of explanatory, but I don't know how to properly use them. But in any case, like, we can see the square wave over there. And that's how you'd normally use an oscilloscope, right? You plot the voltage of a signal over time with varying voltage scales and time scales. I can also do this neat thing with the illuminate the grids, but I won't do that for the rest of the video. Right, but one of the things that's, well, actually before that, you can think like we can draw stuff on this, right? If we know the X position of the beam, we can sort of modulate it up and down so that it draws the outline of something, and maybe in multiple passes we take different paths and draw multiple lines. But there's a much better way to do graphics on the oscilloscope, and that is using this external X input. So basically, this was one of the features I was really interested in the oscilloscope when buying it. Besides having a varying time scale, you can also sort of, if you turn it all the way to the left, we can see now that the beam stays put horizontally, and that's because instead of using the time to move from left to right, it uses whatever signal we put over here. And that's pretty neat, because now we can generate two signals, one for the vertical axis and one for the horizontal axis, so that they walk the beam all over the screen and draw something neat, right? For example, I could you can see that when I approach this banana plug, it sort of moves left to right. It makes a square with Lissajous curve, which is quite interesting. And that's because of the 50 Hz mains noise, as I talked before. And if I actually touch the metal, it will be much greater. There we go. I actually might wanna reduce the gain of the X signal, right? So now what is happening currently is that the multimeter is generating that square wave, which goes in here and controls how high or low the beam is, and when I touch this, the voltage I induce over there controls how much to the left or to the right the beam is, right? And we see these shapes. Now, to actually get graphics and not just plotting noise, we can use some sort of a circuit to generate these two signals, and I am using this Arduino. I could have also used, I also have a Uno. 1 second, right? I also have this Arduino Uno, and it might have worked. Well, actually, it would have worked relatively well, but it doesn't have as many pins as I would have liked. Basically, it has 14 digital pins, and that means I would have gotten like 7 bits resolution on each channel. And now, why is that? I'll talk a little bit about what a digital to analog converter is and why we need it. Right? If you've played around with Arduinos, you might know they can't actually produce an analog signal. Right? The pins can only output 0 or 5 volts, well, 3.3 in some cases, but yeah, the pins have a digital output. They can only be fully low or fully high. And if we were to plot that, we'd basically have control over is the beam left or is the beam right, right? Left is 0, right is 1. But we want to be able to have, to control the beam somewhere in between there. Now, you should note that the Arduino sort of can control LEDs and motors and stuff in an analog fashion, but that's using pulse width modulation, which basically means it turns it off and on and off and on and off and on very quickly. It's in such a way that overall it's sort of turned on 50% of the time and off 50%, or on 75% and off 25%. But on the oscilloscope that would still look like it's just switching from left to right, left to right, left to right instantly. So we need another solution. And basically here I have two such circuits. They are called digital to analog converters because the Arduino gives us a digital signal, but we want an analog one. One of them is built into the board, and that's why I really like this board, the MKR Vidor 4000, because on port A0 it actually has analog outputs, 10 bits resolution, and I didn't have to do anything. I can just code it, and this blue wire will get that signal between 0 and 5 volts depending on what number I give it. Right, so if I give it 0, it puts out 0 volts, and if I give it 1023 in the software, it puts out 5 volts. Supposedly it has a little bit lower limit. But as we know, we need to control both the horizontal and vertical axes, so I need to have two digital to analog converters. The first one being this blue one, and the second one being this circuit I built on the breadboard here. Basically, we can see there are 1, 2, 3, 4, 5, 6, 7, 8. Did I count it right? Yeah, I connect 8 pins to the breadboard, and through those pins I can sort of write the binary representation of the signal I want to put out. So for example, if all the pins are set to 0, it's pretty obvious that no matter what the wiring is here, the output, which is this green wire over here, will also be 0, right? Because it's some sort of combination of the zeros, but adding zeros, even if you multiply them with some factors, still yields a 0. If I set them all to 1, or like 5 volts, basically all of them will be 1, and the output will also be 5 volts. But due to how these resistors are wired up, I can sort of send over these bits, I can sort of send a binary value, like a certain pattern of zeros and ones, and each pin will sort of control different power of 2 in the output signal. So for example, this leftmost bit controls whether the signal is in the first half of the range or in the second half, right? If it is 0, our signal will be maximum 2.5. If this pin is 1, our signal will be from 2.5 to 5 volts. The next one controls sort of in which half of the previous half we are, and so on. Basically, if I write a binary value over here from 0 to 255, I will get a proportional analog value at this green wire from 0 to 5 volts. And by quickly sending matching values, one on the blue wire and one on the green wire, that match to some coordinates on this, like in 0.5 volts, which will map to a position on the screen, I can basically move that point in whatever pattern I want, and it will draw something. So, oh, and before I power it up, I will also mention that this sort of DAC circuit is called an R2R ladder, because all of these resistors, like this top row of resistors has twice the value of this bottom row, and these are R, 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 R. These are 2R, 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 2R. If we say the resistance of these is R, but that's not very. It's sort of relevant, but not very important. All we need to know is that we write on the pins the binary value we want to display, and this ladder of resistors will turn it into an analog value on this green pin. So let me wire up these two banana plugs into the external X and the green output, which is the vertical output, into the probe, and we'll see at what it displays. Right, there we are. I've connected the probe to the green wire and the blue wires go into the external X. And basically now the Arduino, I've pre-programmed it with a path and it outputs that path to the X and Y coordinates of that path to those wires. Before taking a look at the actual display signal, here's what the the Y coordinate looks like, right? Let me scale it up a little bit, position lower, right? We can see it sort of jumps weirdly, but the magic happens when we also coordinate this up and down signal. Instead of using the time from left to right, we use the blue signal to control how left or right it is, and there we go. This is the path I've programmed it, and it basically walks a point along this path and sort of jumps between the letters as many times as it can. And because this is a CRT screen, right, that point has a little bit of persistence. You've also just seen it shift left to right, and I'm pretty sure that's because the capacitors in this oscilloscope are so old and so leaky. Yeah, and it's not a precision instrument anymore. It's so old. I have to fix it someday, but it isn't currently fixed. Right. Maybe change a little bit, play around with the focus. Yeah, good enough. So one thing I'd like to show is how, if I slow down the Arduino, you will be able to see sort of the point walking across these. So give me 1 second to change the code, add a little bit of delay each iteration, and I'll be right back. Here we go, I've just programmed it, and right now you can see sort of a slower motion view of what it's doing. I can slow it down even more, maybe 10 times more, by adding more of a delay between when it moves the points. And yeah, you can now see the point sort of moving. Now I'd like to also show why, like at the beginning I told you that the Arduino Uno had too few bits to actually draw a quality image, right? It would look choppy with only 7 bits per channel, but I want to show you exactly how choppy that is. Maybe you want to build this yourself and don't want to shell out like $70 for Vidor, and there are Uno clones which are dirt cheap. So let me, here's the code. Oh, I should actually, well, never mind, I will put the, no, sorry for the quality, I actually won't put the actual screen capture here. Basically I can set all of the points to be and not 3. That will cut out the bottom 2 bits. Actually I need to set the Y position to cut out the bottom 2 bits because I have the bottom bit for the Y position and the bottom 10 minus 8 2 bits for the, yeah, I think that's good enough, and I'll program it. Hopefully it works. Basically our resolution will be halved. Oh, and I will have to remove the delay so that it draws properly. You can now see the image is a little bit more choppy, right? The steps in the horizontal and vertical directions aren't as smooth as they were before, because now like every bit we add sort of adds another level at halfway between two existing levels, and when we eliminate a bit, we sort of have to jump from 2 to 2 or 4 to 4 levels and so on. And you can see it's a little bit, its resolution is a little bit less, but it might still be acceptable, and such a result would be achievable with an Arduino Uno or some other board which has only 14 bits. But I will now go back to the 10 horizontal bits and 8 vertical bits precision, and also show you some other SVGs I've made, as well as how I'm programming them into the Arduino. So here's the jankiest setup. I'm sorry I'm not using the screen capture, but I really want to make this video as quickly as possible. I've already wasted a few hours trying and not achieving anything. Right, so I have this SVG of the HTSP logo, and also a short little JavaScript script which sort of walks along these points and gives me an array of their coordinates. I will copy that and put it into another script. Here's a Python script which only needs me... Oh, oops, I copied that wrong. I have to open it up and copy object, not message. Paste it over here. Basically, this is a fat array of points, and this Python script remaps them from their coordinates to 8 and 10 bits respectively. And this is the output of that Python script, basically a long list of points as well as a point count variable, which I only have to copy into the Arduino IDE. Replace this part of the code, and now if I compile and send it to the... Oh, I didn't... Oopsie. Oops, that's wrong. Replace this part of the code. Right, it worked, and now we should see that SVG from earlier, and fantastic, it works. Let me play around with the gain a little bit so it's clearer. And also I'd like to show you something which my digital to analog converter sort of does wrong and the built-in one doesn't. Right, you can sort of see these spikes, these vertical spikes, but no horizontal spikes, and these are a design issue in the R2R ladder DAC. Basically what happens is that, and you might be familiar with this issue from like the reasoning why gray codes exist. What happens is that when we go, for example, from the lower half to the upper half, as we can see over here, right, this spike here, it's sort of midway vertically, the bits of the output don't change instantly, right? They sort of change in a ripple pattern or however, and that means like the maybe in this case the most significant bit changes first, right? And it sort of makes the output jump down, and then when the other bits change as well, it jumps back up where it needs to be, right? But we can see halfway and at the quarters we have these sort of glitches. These are called DAC glitches, and well, gray codes fix this, but there aren't any easily implementable gray codes digital to analog converters, well, at least as simple as just a bunch of resistors connected like so. So we'll have to live with these DAC glitches. But yeah, here's another SVG. I'll also upload another one, which is the logo of another team. And let's compile it now. It's uploading, and here we have another cute little logo, which I can adjust. Can I? Ah, yes, I can. Right, to properly display. And here you can see another kind of glitch, right? Besides the DAC glitches, which are vertical and sort of those jumps, you can see over here this trail. I'm pretty sure this is because at the end, like the path goes from this, sort of draws the W and then each letter, and at the end is that it has to jump all the way from here back to here, and I'm pretty sure that's what's happening. Like it's somewhere around here, and then the signals, of course the signals don't change instantly because of inductance and resistance and capacitance in the wires, as well as just, well, everywhere in the circuit. They can't just immediately jump there. It sort of goes like this, and you can see the trail it leaves. So if you want to have cleaner images, you have to sort of plan your path so that it doesn't have these sort of long jumps. For instance, in between the letters, you can sort of see small little jumps over there, but they aren't as noticeable because they're small. So optimally, maybe the path should go something like, I don't know, maybe go to the W like this, and then draw the letters from right to left, and maybe even this part of the W, draw it at the end, so that it's sort of continuous, it doesn't have these big jumps. But yeah, that's about it. In the future, I will like to make some animations, also make a better some software which actually automatically converts SVGs or some other format to Arduino programs, so that I don't have to like copy between 4 different programming languages. And also maybe design a compressed communication protocol so that I can upload real-time images from the computer to the Arduino without wasting too much time, right? Because I think uploading such a list every frame would be too slow, and you would actually see like it draws it and then it waits a bit for the upload, and then it draws it again and waits a bit for the upload, and that wouldn't work. But with some compression, I think it's certainly doable. So yeah, stay tuned. I will make some other videos on what me and my colleague managed to do in the future with this project. But as far as it's as I've done up to now, I think it's pretty cool already. Cheers!